Hello everybody, this is Josh with Incompetech, and today we're going to be talking about some technology that was used to help bring about the ability for things like the internet to be created, for things like your home network to be able to work, and obviously companies to have their own networks. The OSI model and how it works, what it was designed for, and how it actually helped bring all of that together. So what is the OSI model? So the OSI model is a standard created by ISO in 1984. And it's not anything tangible. You can't go out and download the OSI model. You can't go out and install the OSI model. You can't really do anything with it. You can't feel it, touch it, anything of the sort. It's just a framework to explain how to deploy protocols that help computers and computer systems communicate with each other. So there's no real data to be gathered or to touch or to manipulate. It's really just a framework that everybody used at some level to configure their application or their network device to communicate. It's not actually used by a lot of people that make equipment, but they fall in line somewhere in the 7 layers. And there are 7 layers, just so you'll know. It said, and on one of our bullets over here, it says right here, there are 7 layers. But they'll follow, because not everything uses all 7 layers, but they'll follow what that framework said for the layer that they're working at. So, what are the layers? Obviously, we have them here on the list. There's the physical layer, data link layer, a network layer, a transport layer, a session, presentation, and an application layer. All of these layers have something specific that they do with how computers talk to each other, and how the application, all the way down to the physical layer, what happens at each layer and what that layer is supposed to do. So, as I said, it was developed by ISO in 1984, and a lot of systems that we use today still follow this basic guideline, but nobody really actually ever deployed the full 7 layers, because there's certain stacks of information that build upon each other that create how a computer works today, and each of those stacks was devised around specific portions of this layer, but not all of it. So, as an example, some applications will send their information to a portion of the operating system that will then in turn send it to the network interface card for the application. So the application doesn't have to understand how to break down the data that was created by the user so that the network interface card understands it. The OS does all of the work for it. So like I was saying, not everything that is built for a computer actually does every single part of this OSI model. There's certain pieces that are done by certain parts of the system as a whole. So let's move on. A lot of people who are in the business had to memorize this. I know I had to memorize each layer, what they did when I was taking a lot of the tests, and some people use different mnemonics. I always use this mnemonic on the left because, well, I like sausage pizza. So please do not throw sausage pizza away. Physical, data link, network, transport, session, presentation, and application. That is how I always remembered it. Whenever I sat down to take a test that required me to know the OSI model, the first thing I would typically do is get my scratch paper and my pencil and write out, please do not throw sausage pizza away, and then write, okay, well, I know that the away is application, that the P is presentation, the S is sausage, or the S for sausage is session, the T is transport, the N is network, and the D is data link, and the P is physical. That way, when it came time to look into the questions, I would have a reference there that I knew top to bottom without having to think about it too hard, real quick, what the 7 layers were and the order they were in. So, layer 1 is called the physical layer, and it describes specifically how the electrical connectivity works and or the light waves will function, because not everything is electrical, right? There are some network connections that are light. So you take an optical cable and plug it into the back of a network card. The network card converts the electrical into a light signal that then gets passed along this piece of fiber optic to the far end, that then converts the light back into an electrical signal. Well, the physical layer of the OSI model describes all of that. And it works with the cabling, like I just said, so it could be Cat 5, Cat 6, Cat 3 back in the day, Cat 1, 2s. It could be fiber optic. It could have been coax, because, you know, in the beginning, that's what a lot of the networks were, coax. It also talks about how the network interface card works. Hubs and connectors all work in the physical layer. And at this layer, all the datagrams are considered bits. Ones and zeros. So everything gets converted into a 1 or 0 as it hits the wire. And then we have the data link layer. The data link layer provides connections between hosts on the same network. So if I have 2 computers sitting here connected to the same switch or hub, they can talk to each other via the data link OSI layer. And that's done because every PC network interface card has a specific unique MAC address, and MAC addresses are on the data link layer. So when a computer talks on the data link layer, it sends out its MAC address, and if it knows the destination MAC address, it puts it into its frame and says, here's my source, I want to talk to this destination, and then a payload that it's sending to it. Most systems don't really use the data link layer in that function. Most systems, even on a local area network where all the computers are talking on the same physical network, really don't ever use the data link layer for communication, because it doesn't really have all of the required protocols for things to work. But they still can, and they do. And if you ever have the opportunity to sit down on a network with a sniffer and look at all of the packets traversing the network, you'll see that there will be some data link frames from computer to a broadcast address that all the other systems then look at. Now, this is also where switches work. Switches read those MAC addresses and store those MACs in a table, and then say, well, all right, I know that MAC is on this port, and this MAC is on port 2, and this port has, this MAC on it, so forth and so on. And datagrams at this level are considered frames because they are framed out. They have a specific header value with a source MAC, a destination MAC, and some other details in it. We're not going to get into the details of all of that. I'm just giving you some base information to understand. So layer 3 is the network layer. The network layer provides connections between hosts that are not on the same network, i.e., my computer sitting here talking across the internet to Google's web servers. This is where layer 3 works. So it's all based on IP addresses. So I'm sure most of you know, if you've ever had any issues with your home computer and had to call or home network and had to call your local provider and say, hey, my network's not working, I can't get out to the internet, etc., etc. And they may say, hey, pull up your command prompt and type ipconfig/all or just ipconfig and tell me what your IP says. So everything in today's world has an IP address that talks on the internet or a home network or a computer network at the office. Those IPs are very specific to where they're connected, and they're typically unique unless, like most houses, right, everybody kind of has the same basic setup. Most of them will have a 192.168 1 dot something or 2 dot something address on their computer and for within their network. But the router that you connect to that goes out to your internet service provider does what's called NAT, which is network address translation, which takes those 192.168 IPs and hides them behind a public IP that's on the router that can be routed across the internet. We're not going to get into a lot of detail, but that's basically how that works. And most companies have sort of the same premise because most companies don't have enough public IP space for every computer on their network. So they use another class of addresses, 10 dot something, that's not routable on the network. And then they hide it behind a IP or group of IPs that they have routable on the internet for their company. This is where the OSI Model Layer 3 comes in, is at the IP address layer. Routers that route those IPs are all working at Layer 3. The datagrams here are called packets. The transport layer. The transport layer is where the majority of the protocols that we use today functions. TCP, for example, is going to probably be the #1 protocol used by everybody that's watching this video or everybody that will watch this video, and I'll tell you why. Everybody surfs the web. HTTP and HTTPS both run on TCP. TCP stands for Transmission Control Protocol, and it runs in the transport layer. UDP also runs in the transport layer. Port numbers, which both TCP and UDP use, is part of the transport layer. This is where you get end-to-end connectivity. End-to-end connectivity being my computer on TCP port 32768 connected to Google's computers on port 443, which is HTTPS, for me to surf their web. Flow control also occurs here. Reliability, because in TCP specifically, it is a reliable protocol, meaning it makes a full handshake connection to the far end computer that you're talking to. And if packets get dropped, both ends know it, and the end that didn't receive the packets will tell the end that sent the packets, hey, I didn't receive packets number 4 and 5, please resend, and the sending computer will do that. That's the reliability. Then here, the datagrams are called segments. Now, real quick, the top 3 layers are all going to be called, for datagrams, upper data layer. I don't know why they decided to do it that way, and it really doesn't matter, because, like I said, nobody really ever touches all 7 layers when they're configuring their application or they're designing their product, because they depend on the OS or some other lower level configuration that's already been put in place to do a lot of the transport or packet or the segmentation or the framing or the forming of the bits onto the physical layer. Their job is mainly, hey, let's put this program together that the user can do their work and send the data or whatever the case may be. So here at session 5, or at layer 5, is the session layer. And this is where you start and stop sessions. It controls the dialogue between the 2 computers, or however many computers are talking. Controls duplexing, termination, and restarts. And like I said, the datagrams for this is going to be the upper data layer. The presentation layer, layer 6. This provides context for the communications. And by context, it means, hey, this is going to be ASCII characters that we're sending. This is ASCII characters that we received. That type of context. It's the format of the data. It's if it's not ASCII, it could be EBCDIC. So it's all depending on what the two computers can talk and what the application was configured to do. This is where also you can encrypt or decrypt data. You can compress that data down and, of course, decompress it. And, of course, the last layer, layer 7. Layer 7 is where our network applications work. And by network applications, we're referring to applications that were specifically designed to have some network requirement, like SMTP, FTP, and Telnet. All three of these were designed specifically to work on or across networks. SMTP is what you use every time you send an email via Gmail or Hotmail or AOL Mail or whatever mail system that you use, or your ISP's mail system. When you click send after you've typed up your email, it sends it to an SMTP server, which stands for Simple Mail Transport Protocol. What the SMTP server then does is it looks up in its SMTP information, and some of it could be using other information like DNS, which it will use, who that email is destined to. It will then go out and find the server that is the SMTP server for the domain that you're trying to get that mail to. So if it's Gmail sending email to AOL, Gmail servers will look up the AOL servers, then make an SMTP connection to the AOL servers, forward the mail to the AOL servers, wait for the AOL servers to reply stating, yep, we've received it, yes, it's valid, and then close the connection. FTP is kind of the same. You've got an FTP session where you've FTP'd into a server to either upload or download some files. And Telnet is a protocol that is used to get a command line prompt to some device, whether it's another computer or a router or a switch. And it's the same concepts where you've got some device sending an open request to open a Telnet session to another device. And all of that's happening at the application layer for the user interface. But because these were designed as network applications, they actually use the majority of the top three and then depend on the OS to do a lot of the last four layers. And again, last application layer is considered an upper data layer. Now, the flow between systems, as I've been discussing, I haven't really been able to show it to you yet, but that's what I'm going to try to do here. So the flow between systems starts with a sending system and a receiving system. So our sending system here on the left wants to talk to the system on the right. So what happens is an application builds this data by the user either typing an email or whatever the case may be, and sends it. The application itself sends it out. Well, now the OS has some work to do, so it takes it and sends it to a presentation layer, which it then in turn puts another piece of information in front of the data, and then that then drops down to a session layer, which then attaches another piece of information onto the presentation layer's information and the data that came from the app. Then, of course, the transport layer does the same thing. It attaches some details in front and says, hey, all right, the transport layer, this is what we're doing. The network layer then attaches a header on that says, my source IP is this, and my destination IP is either a known IP or some IP that's not known, in which case we'll just send it out to our local router. The data link layer in turn does the same thing, except it does it with the MAC addresses. It puts a header on that says my MAC is this, my destination MAC is this, and packages it all up and sends it down to the physical layer. The physical layer then will take all of that electronic information that we just packaged together all the way from the application down to the physical layer and chop it up into ones and zeros. Put it onto the media, whatever the media may be. It could be Cat5 cable, fiber, it could be wireless RF, and sends it across to the other PC. The other PC or other system sees that information coming in and does just the opposite. It now strips off the physical layer information and the data link layer, and strips off the network information at the network layer, strips off the transport at the transport, the session at the session, the presentation at the presentation, and then finally the application gets all of that data that was packaged up and displays it to the end user. That's simplistically how data gets from computer to computer based on the OSI model. There's really not a lot to it. There is a lot of detail in each section and each layer of the OSI model that I didn't go over. I spent probably over the last 20 plus years in computers months trying to memorize pieces of the OSI model that I couldn't, wrap my head around. And it all comes down to just understand the basics of how a computer talks to another computer with the OSI model. Going back to this, just understand that each layer has its job and function, and know which layers have what job and what works at those layers is the important part. If you can remember that, you can pretty much do anything on a networking job, anything on a network in general. All you got to do is remember the OSI model, how it works, where the problem's at, and you can pretty much solve the issues. Now, in conclusion, though, what we have here is just a reference model called the OSI model. And it was designed so that disparate systems could be able to communicate with each other, because prior to the OSI model, non-like systems couldn't communicate to each other. So if you were HP and you built this system for college XYZ, because back in the day that's really all that had, these types of systems and had networks, or the government, and Unisys built a system and put it at the same college on the same network, those two systems couldn't talk to each other because they weren't built with the same information inside them to say, when you're building this package and sending it onto the wire, here's how to do it. They all did it their own way. So if you were a college or the government and had a network, you either bought all HP, or you bought all Unisys, or you bought all DEC equipment, or Compact, or whatever the case may be. You didn't stray from that, because if you did, that system or group of systems that you bought that weren't the same as the others couldn't function or talk to the others. When the OSI model was designed by ISO and everybody started paying attention to it and writing their applications and their code and their systems to function within that framework, systems that were not created or were not designed by the same manufacturer could now communicate with each other. So HP and Unisys systems could talk to each other, Compact and Unisys could talk to each other, DEC and HP could talk. It didn't matter what you were at this point. Everybody could communicate to each other. And that is what exploded into the internet. And to be honest, it was amazing when I started in this business to see how fast the internet grew over the years, and knowing how the OSI model came into play for this. I remember when the first computers that we had in the military hit the submarine force, and it was just interesting, and that's what drove me to learn this stuff, is because of that, seeing those systems coming on board and having to deal with them and know what they were. And I was thankful to at least have a base knowledge of it already when they hit the system, or when they hit the ships. And then getting out and getting more involved in networking to the point that I am today, learning the OSI model, it threw me back to go, oh, so that's why we were able to not have to buy all like systems, because even in submarines, everything was either manufactured by a single manufacturer until the Navy kind of made this one system that made it kind of possible so that other systems could talk to other systems that weren't made by the same manufacturer. And part of that came about because of the OSI model. So, to conclude, I hope you enjoyed the presentation. If you have any comments or questions, please feel free to drop them down in the comment box. And if you liked it, give me the thumbs up, and hope to see you on the next one.